Hello and welcome back. We're going to talk about sampling distributions today, and this is a concept that really comes about and leads us to the law of large numbers, which is the central limit theorem. So let's talk about the key components here. We're going to understand the concept of what a sampling distribution is, which is the distribution of all the values of a statistic when all the possible samples of the same sample size are taken. That's a lot of words, but we're going to do an example to make it make more sense as we go. We'll also see that some statistics are better than others for estimating population parameters. Well, that's the whole reason for taking all the samples, is that we can then estimate the population, whether it be the mean, the standard deviation, variance, range, etc. So the sampling distribution of a statistic, it's important to realize that it's every possible sample of some sample size that you've predetermined are taken from the population. So you can begin to imagine that if you have a, say, population that's a huge population, and then you start taking samples of all different sizes, wow, you could be here for a really long time. So the ones we're going to do are very small. We're only going to have 3 items in it. When we do that, though, we can get a sample means, and that has to be from all the samples having the same size. The sample mean does target the population mean. So that is that we could take many samples of the same size, look at their means, then take the mean of means so that that would target or give us a good estimate of what the population mean would be. The distribution of the sample means, it tends to be a very normal distribution. We can also do the same thing with variance. Take a distribution of all the sample variances. And if we do that, we're going to find that that sample variance does target the value of the population variance. The distribution of the sample variances tends to be skewed to the right. So we need to have a way to distinguish between a population proportion and some sample proportion, because a sampling distribution of proportions can also be taken. So we're going to use P for the population proportion and P hat for a sample proportion. Sample proportions, again, do target the value of the population proportion. Very important thing, because that allows us to estimate that population proportion. The distribution of the sample proportions also tends to be a normal distribution. Unbiased estimators, that means that they are good estimators that can be used for the population parameter, and those are the sample means, the variances, and the proportions, and we just talked about all those. These statistics are better than the other ones we're going to talk about in estimating the population, because then we have biased estimators, and those are not good for targeting the population parameter. So those are sample medians, ranges, and yes, standard deviation. Now, there is a note down here, because we are going to use the standard deviation, because it is if it's relatively small. So we can use that, and it's often done so in the industry and any kind of data science. So here's an example that was put together where we rolled a die 5 times. We find that the mean X bar and the variance and the proportion of odd numbers of all the results. So let's take a look at what happens. So here's 10,000 trials that were done. So we have a sample, our first sample had a mean of 3.4. Our second sample had a mean of 4.4. Our third sample had a mean of 2.8. And we could go on over and over and over again. In this particular one, it was 10,000 trials. That means 10,000 different samples. 5 rolls of the dice and find out what their mean is by adding up, of course, and dividing by 5. Well, as you continue to do that, and the more trials you take, the more and closer you get to the actual mean of the entire population. So 10,000 trials is going to really get us close to the measure of center, the mean or the population mean, mu. Also, anytime you have that, you're going to have a sampling distribution that is normally distributed. The same thing here was done, but this time with variance. All those 10,000 trials, we found the sample variance. And again, that will approach the population variance. However, this distribution is skewed right. The same thing again with proportions. Took all the sample proportions. What are the odds? And odds is a probability, is a proportion. That is a measure of the mean. You're going to get to that the more samples you take. And the distribution is a normal distribution. So a little note about replacement with and without replacement. Well, in our sampling, we're always going to do for 2 reasons. One, if it's a very large population, it's not going to matter anyway. There's going to have little effect on the total outcome of our statistic and what we calculate. Also, by sampling with replacement, we will have independent events. That means that they are unaffected from the previous outcome. And they are much easier to analyze and result in simpler calculations. So we will be using replacement. Caution though, many of the methods are simple random samples, but as you know and have learned earlier, it can be that the samples are bad, voluntary responses, convenience samples, etc. And you know what to look for there. So let's take a look at what this all means. So we're going to have a very small space, because if not, we would be here all day. And we're going to have the numbers 4, 5, and 9. And we're going to take a sample of n equals 2. Now I have to take a sample of every possible sample, has to be listed, from n equals 2, taking 2 from the 3 that's there. So let's make a column here that says sample, and we're going to do our sample mean. And we'll go ahead and say what's the probability. So with replacement, remember, with replacement. So my first one is 4, 4. Then I could do 4, 5. Then I can do 4, 9. Then I could do 5, 4, 5, 5, 5, 9, 9, 4, 9, 5, and lastly 9, 9. So I have that 4, 5, and 9 number. Remember, I'm going to pull samples with replacement, and I'm going to write down my sample space of every possible sample. Now, very quickly, we'll go in here and we'll write down the sample mean. That means I'm going to add 4 plus 4, get 8, divide by 2, of course, is 4. Adding 4 and 5 for 9, divide by 2, will give me 4.5. And we're going to go ahead down here pretty quickly here, and I'll do these as fast as possible. And you can see all I'm doing is adding them up and then dividing by 2. And 9.4 and 9.5 is 7, and 9.9, of course, is 9. So if we count these, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 samples, they all have an equal probability of being selected. That's a simple random sample. The probability then is 1/9 of each. And of course, that probability will add to 1. So when I now look at this, I want a mean of the sample means. So that means I would add all these numbers and then divide by n, which of course is 9. And that would give me my mean of the sample means. Of course, it means the average of all those samples averages. So let's go ahead and pull up our calculator here. We can add them up by hand. We could put them into list 1. So my calculator might be finicky here on coming up. It is being finicky. Okay, so we could simply add them all up and divide by 9, or we can also use our list. We can edit our list. I can go in and put, whoops, not 44, 4 would be a little bit better there. Just add these to my list. Okay, now that I have them in my list, what's nice is I can go ahead and get out of that list, then go to stats, run my calculation on one variable stats, just like we've done before. We know it's L1. There's nothing in our frequency list, so we're going to leave that blank. And then we're going to hit our calculate, and it's going to give me all of those statistics. So the mean of the sample mean is 6. But we can also get our sample standard deviation. We could also get our quartiles, and of course the median, and then the range. So this whole section is really just to prime you and have you think of pulling samples of every sample of a certain size from a larger data group and then getting a mean of the samples and finding what its standard deviation is or its variance is, etc. That is all for this section.